Hello everyone, it's my honor to introduce our ICSE paper, Coca, Improving and Explaining Graph Neural Network-Based Vulnerability Detection. Software vulnerabilities are weaknesses that could be exploited by a threat actor for a variety of malicious ends. Prior studies rely on human experts or predefined vulnerability rules to search for security-sensitive operations. After that, a series of dynamic techniques such as fuzzing and symbolic execution are developed to automate this process and have achieved promising results. Benefiting from the great success of deep learning in code-centric software engineering tasks, an increasing number of learning-based intelligent detection approaches have been proposed. Compared to traditional approaches that heavily rely on handcrafted vulnerability specifications, deep learning approaches focus on constructing complex neural networks to automatically learn implicit vulnerability patterns from source code without human intervention, while demonstrate superior performance. Due to the black box nature of neural network models, deep learning-based approaches fall short in the capability to explain why a given code is predicted as vulnerable. Such a lack of explainability could hinder their adoption when applied to real-world usage as substitutes for traditional source code analyzers. To review the decision logic behind the binary detection results, several approaches have been proposed to provide additional explanatory information. As the pipeline shown below, given a to-be-explained vulnerable example and black box model, they perform program reduction to search for the minimal suspicious statements that retaining the initial model prediction. In this work, we focus on GNN-based vulnerability detection approaches because they have shown better capability in this domain. However, these approaches face two challenges that limit their potentials. Firstly, most approaches follow the perturbation-based mechanisms to provide justifications for individual predictions. The high-level idea behind this approach is to search for important features, positively contributing to the model's prediction by removing or replacing a subset of the features in the input space. Perturbation-based explanation techniques assume that the detection model is quite robust. That's to say, these removed or preserved statements are consistent with the ground truth. Unfortunately, as reported in recent works, simple code edits such as variable renaming can easily mislead neural network models to alter their predictions. As shown in the code example, the explanation is a statement at line 3, which is a variable declaration, while actually the statements at line 20 to 22 are the root cause of the vulnerability. Therefore, due to the weak robustness of existing deep learning-based vulnerability detectors, their explanations are easy to be altered due to small perturbations or even random noise. As a result, explanations built on top of the detection results from such weakly robust models just reveal spurious correlations, which are hard to be correlated by security applications. Secondly, most prior methods focus on the maximization of mutual information theory to generate explanations from the perspective of factual reasoning, providing a subset of the input program for which models make the same prediction as they do for the original one. However, such extracted explanations may not be concise enough, covering many redundant statements which are benign but highly relevant to the model's prediction. Therefore, it still requires extensive manpower to analyze and inspect numerous explanation results. As shown in the figure, the SODA factual reasoning-based approach, GNN-Explainer, provides more nodes and edges as explanations. In conclusion, factual reasoning-based techniques favor a sufficient subset which contains enough information to make the same prediction as they do for the original program, while counterfactual explanations may only cover a small subset of the ground truth. As a result, existing GNN-specific explanation approaches fail to balance the effectiveness and conciseness. To address these challenges, we propose Coca, a novel framework to improve and expand GM-based vulnerability detection systems by combinatorial, contrastive learning, and dual view causal inference. The key insights underlying our approach include enhancing the robustness of existing neural vulnerability detection models to avoid spurious explanations, as well as providing both concise and effective explanations. For the sake of conciseness, we refer them as trainer and explainer later. This figure depicts the architecture of our trainer. In this stage, we aim to train a neural vulnerability detection model that's robust to random perturbations. Trainer augments the vulnerable or benign programs in the dataset into a set of functionally equivalent variance via thematics preserving transformations. In this work, we apply the following 6 token or statement level augmentation operators introduced by prior works to construct happy program variants. Then we leverage combinatorial contrastive learning to force the detection model to focus on critical vulnerability thematics that are consistent between original vulnerable programs and their positive pairs, instead of subtle perturbation. The total contrastive loss is formulated as follows. To derive explanations on why the detection model has decided on the vulnerability, we propose a model-agnostic extension based on the detection results. Similar to the most related work, IVDetect, we aim to find a subgraph which covers the key nodes and edges that are most distinct to the prediction label. The main difference lies in that we aim to seek both concise and effective explanations. Hence, we propose a dual-view causal inference framework, which integrates factual with counterfactual reasoning to make a trade-off between conciseness and effectiveness. Formally, the extraction of subgraph can be formulated as follows, where the objective part C measures how concise the explanation is. It can be defined as a number of edges or features used to generate the explanation subgraph G. The constraint part SF reflects whether the factual explanation is effective enough, while SC reflects whether the counterfactual explanation is concise enough. Then we jointly optimize the objective part and constraint part. The detailed formulation can be found in our paper. Since the detection capability of deep learning-based models benefits from large-scale and high-quality datasets, we built our evaluation benchmark by merging 5 reliable human-labeled datasets collected from real-world projects, as shown in the left table. We consider 3 state-of-the-art GM-based vulnerability detectors as baselines, as shown in the right table, compared to traditional cross-entropy-based training strategy. Our combinatorial contrastive learning comprehensively improves the performance of existing GM-based vulnerability detectors in terms of all evaluation metrics. We attribute the improvements to the robustness-enhanced models truly picking up real vulnerability features for prediction. Taking the greatest improved model Dibugon as an example, as shown in the visualizations in the below figure. The feature representations learned by Coca are more class discriminative compared to the ones learned with default cross-entropy loss. In addition, we can observe that detection models which are trained with traditional cross-entropy loss outperform their variants trained with self-supervised contrastive loss, such as InfoNCE and NCE. It's reasonable because fine-tuning on the labeled vulnerability dataset may significantly alter the distribution of learned features representations. As a result, the robustness and accuracy of learned representations enhanced by self-supervised pre-training may no longer hold after supervised fine-tuning. On the contrary, the supervised contrastive learning allows us to effectively leverage label information, which groups the samples belonging to the same class as well as the thematically equivalent variants, while simultaneously pushing away the dissimilar samples. Accordingly, the downstream task specific, generalization, and robustness can be retained as much as possible. Second, we investigate whether Coca is more concise and effective than state-of-the-art baselines when applied to generate explanations. We adopt three recent vulnerability explanation approaches as baselines. There are mValParator, IPDetect, and P2IM. To evaluation, we use the fine-grained vulnerability triggering path metric to evaluate the quality of explanations. The right table shows the performance comparison of Coca with respect to SOTA explanation approaches. As can be seen, based on the predictions of popular graph-based vulnerability detectors with default implementations, Coca substantially outperforms all the compared explanation techniques on all metrics. In addition, there is still a certain gap from our best-performing Coca. We find that the performance of each explanation baseline can be improved to varying degrees when applied to robustness-enhanced detection models. The requirement for explainability is more urgent in security-related applications. In this work, we analyze the limitation of existing explanation approaches for GNN-based vulnerability detection systems and propose Coca, a general framework to improve and explain them. By applying and evaluating Coca over three typical GNN-based vulnerability detection models, we show that Coca can effectively improve the performance of existing GNN-based vulnerability detection models and provide high-quality explanations. Thanks for your listening.